We are now going to look at the length of a smooth curve y equals f of x. I'm going to start off by giving you the formula. The length of a smooth curve is equal to the integral from x equals a to x equals b of the square root of 1 plus quantity dy dx squared, and then outside the radical dx. That's also equal to the integral from a to b, the square root of 1 plus f prime of x quantity squared. Same thing, different notation, outside dx. We're going to work out a couple examples where we utilize the formula, and then we will end this lesson as we develop or derive this formula. In question 1, we revisit this eyeball, football looking bounded region between y equals cosine x and y equals natural log of x squared plus 1. So this bounded region here we will call R. This is region R. And in question 1, it says write an expression involving one or more integrals that gives the length of the boundary of the region R. Do not evaluate. Now when you hear length of boundary of region R, a Morley word for that, Morley expression for that would be the perimeter of R. The perimeter. So we need to find the perimeter of region R. So perimeter is simply the sum of the length boundaries. So in logic, what we need to do is we need to find the length of the blue curve here. We need to find the length of the yellow curve here, and we need to add the lengths in order to get the perimeter. So I will use blue to write an expression for the length of the blue portion of the perimeter. So I'm using the formula above, so this is going to be the integral from a to b of the square root of 1 plus, now inside the parentheses, the thing that's getting squared inside the parentheses is, as the formula shows us, the derivative. So if I come over in my margin, I'm going to find derivative with respect to x of the blue function, and that of course is negative sine of x. So the negative sine x goes inside the parentheses dx. So next I need to add to that the length of the yellow, and the yellow is going to be the integral from a to b again, this time square root 1 plus, I'll need parentheses, squared dx, and inside those parentheses will be dy dx of the yellow, which is going to be 1 over stuff times the derivative of stuff. Okay, so I can write that as 2x over x squared plus 1, and again, according to the formula, I need to square that quantity. And there we have it. That expression gives us the perimeter. Now we're on a new page, so I want to make sure that I indicate what a and b are in the problem. A is the negative 0.916, and the b, of course, was the positive 0.916. So that would answer the question appropriately. Now I'm taking a look at the second example, where we're trying to find the length of y equals the tangent of x from negative pi over 3 to 0. So I'm ready to do this. I'll start off by finding dy dx, as I know I'll need that in my formula, and that should be easy enough, the secant squared of x. So now my length equals the integral from negative pi over 3 to 0 of the square root of 1 plus the secant squared x is the derivative, and we'll have to square that. Outside we have the x. Now this is a calculator active question, and I would like you to try to evaluate this integral using the calculator, because it's not easy. The syntax is very tricky. Before I even do that, let's go from negative pi over 3 to 0, square root of 1 plus, I'm going to write this as secant of x to the power of 4. That will help me to put it into the calculator. So take a moment and see if you can actually evaluate that integral, and once you've done that, you can unpause and see my syntax. So what I would have done is the integral, this is the calculator syntax, I would have then typed the radical button. There's just so many parentheses here. So a radical begins with a parenthesis, 1 plus, now I know I'm going to take the secant of x to the power 4, so I'll need a starting parenthesis, and then I'll need secant. Now how do you get that secant? I always just say alpha s, alpha e, alpha c. By typing in sec, it draws up the secant function. You can also find the secant function in the catalog and perhaps a variety of other ways. Please avoid doing 1 over cosine. It gets so complicated with the syntax. So we have parenthesis secant of parenthesis x and parenthesis. Now I'm going to close this parenthesis because the secant of x will be to the power of 4. Now that ends the radical, and I'll do that with respect to x, and I'll take that from negative pi divided by 3 to 0, end parenthesis. I'm going to use some color here to just make sure I've got this right. So this first set of parentheses is for the x, followed by this second set of parentheses around the secant of x, that gets to the power 4. Next, I'll take a look at the parenthesis for the radical, so we're good here. And finally, I'll use this brown color for the beginning and end of the integral. Now, if you have that done correctly, you will get the answer of 2.057. Make sure you're able to do that. That gives us the length of the secant, gives us the length of the tangent on this interval. Example 3 is a non-calculator, and I would like to see how far you can get with this. This is an interesting problem because y is equal to an integral function. You should recognize this type of integral function. We're using a dummy variable t as the integrand, and this wants the length of this y function from negative pi over 3 to pi over 4. Again, we're going to need dy dx here because that's going to be utilized in the length formula. So the dy dx, or the derivative of y, we go back to the fundamental theorem of calculus part 1. The derivative of the integral gives us back the integrand, substituting the x in. We no longer have a dummy variable. If this x were something other than just x, maybe 2x, we would need a chain rule times 2 outside. So there's the derivative. And now my length is going to equal the integral from negative pi over 3 to pi over 4. In fact, I'm going to say up here a equals negative pi over 3 and b equals pi over 4, so I don't have to keep repeating those. And this will be the square root of 1 plus, now inside the parentheses is this square root, secant squared x minus 1, and that of course gets squared because the derivative gets squared in the formula, dx. So if I simplify that, I have the integral from a to b, square root 1 plus, so I'm squaring the square root, to get secant squared x minus 1 dx. Simplifying further still, I have the integral from a to b, the square root of, well, the 1's canceled out, and I have secant squared x dx. Okay, so then that equals the integral from a to b of the secant of x dx. Now, if I only knew a way to integrate secant of x. Can you think for a moment? Here's a hint. That is a basketball. That is a net, backboard, and a certain basketball player by the name of Jeremy Lin. And if you recall the funny mnemonic for memorizing secant of x, antiderivative. It is natural log, absolute value, secant of x plus tangent of x. And we're going to take that from negative pi over 3 to pi over 4. So I'll use the fundamental theorem of calculus part 2, and I'll have the secant of pi over 4 plus the tangent of pi over 4 minus the natural log secant of negative pi over 3 plus the tangent of negative pi over 3. So this is the natural log. The secant of pi over 4 will be radical 2 plus the tangent of pi over 4, which is 1, minus the natural log. This will evaluate to be 2, and the last one will be negative rad 3. So that's about as far as I'd like it to go. Of course, you could simplify this and radical 2 plus 1 over 2 minus radical 3. That's as far as I need you to go. In fact, I probably wouldn't ask you to go that far. I just think it's really neat that we're combining a bunch of these techniques and concepts throughout the course of the year to find the length of this special curve y. Example 4 is to be done by hand. You're finding the length of the function y from 0 to 3, and we'll need dy dx, which equals, well, let's say we'll take this exponent of 3/2 multiplied to the coefficient of 1/3, and that will give us 1/2 quantity x squared plus 2 to the 1/2 times the derivative of stuff, which is 2x. The 2's cancel out, and that leaves me with x times the square root of x squared plus 2, like that. So now I'm ready to find the length, and the length is equal to the integral from 0 to 3 square root of 1 plus the derivative. Let's be careful with this derivative. That whole derivative gets squared dx, which is equal to the integral from 0 to 3 square root of 1 plus, well, I'll have an x squared, and then the second part, the 1/2 power, will go away. So I have that. Now you can actually do this by hand, but you have to be clever, so maybe you want to pause and see if you can figure it out from here. Continuing on, integral from 0 to 3, this becomes 1 plus x to the 4th plus 2x squared dx. Here's where the real cleverness comes in. You may or may not have recognized this here to be a perfect square. It's the quantity x squared plus 1 squared dx. So then the square and the square root cancel each other out, and we have the integral from 0 to 3 of simply x squared plus 1 dx, and that is a pretty easy evaluation. X cubed over 3 antiderivative plus x, and we will take that from 0 to 3. Plugging in the 3, we get 9 plus 3. Plugging in the 0, we get 0 plus 0, and so the length of that curve is 12. Remarkable and fun. Now let's go back to the page where we are going to develop this formula. We used it several times in the last several examples, so let's figure out why it works. It is likely that this will be on your test, so you want to take careful notes. Okay, so we have established that an integral is an infinite sum of stuff. So if I'm looking at the length of the curve here, the length of this curve here, I want to think of that as the infinite sum of certain geometric objects. So can you think of what geometric object I will infinitely sum to get the length? If you are thinking to infinitely sum these little line segments, then you are sharp. So let's say from point P to point Q would be a line segment, and I want to come up with the distance from point P to point Q. And the distance from point P to point Q would be utilizing the distance formula, which is this change in x squared plus the change in y squared. It's just the hypotenuse Pythagorean theorem. So there it is. That gives us the distance of the little line segment from P to Q. So we're just going to do some manipulation of this, and you hopefully will see before I'm completely finished how this will lead to the formula above. Now I'm going to multiply this by the square root of change in x quantity squared, and to maintain the equality I'm also going to divide by that, the square root of change in x quantity squared. Now why will I do that? Well, on the left part of this, the square root over square root is equal to one gigantic square root, which is then change in x squared plus change in y squared over the change in x squared. And then to the right, the square root of change in x squared is simply change in x. Okay, I'm going to hop a little further to the left here to continue this. So now I have this here is like a common denominator, and because it's a common denominator, I can divide it into each of the numerator parts. So we have change in x squared over change in x squared plus change in y squared over change in x squared. Hopefully, don't forget this trailing change in x, hopefully you can already start to see where this is going. Okay, so I continue to simply manipulate this distance between P to Q. This becomes 1. The change in x squared over change in x squared is 1. Plus, now squared over squared can be the whole thing squared, so change in y over the change in x quantity squared with the tailing or trailing change in x. So that again is just the distance between any 2 points P and Q. So we're going to come over here now. Let's actually scroll down a tad. Okay, and we'll say that the length from A to B is approximately the sum of all these little line segments from P to Q, and each of these has a distance 1 plus change in y over change in x quantity squared times the change in x. Now if I'm being more precise, I'm going to say from I equals 1 to n, from the first segment to the last segment, which would then mean I put these little i's in here, the first change in x and then the second change in x, etc., etc. It's important that you write this step in the proof so that you get the idea that the length is approximately the sum, so that when I say what the length is actually equal to, you can see it as an infinite sum of the segments. So it's the infinite sum from A to B of the square root of 1 plus, now change in y over change in x, infinitely small, becomes dy dx, that quantity squared, and then change in x becomes infinitely small dx. Of course, I really wanted to add over here over interval A to B. So here it is. The length is equal to the infinite sum of little itty bitty line segments. The end.